Okay, let's solve this same problem using a slightly different approach. So I have my transfer function, but instead of going into the frequency transfer function, I'm just actually going to basically get out of transfer function realm altogether and try to get this guy back into my time domain and then solve this problem using some of the earlier equations that I showed you in the chapter. So follow me here. So let's start by looking at what actually constitutes the, you have this displacement and you have the force. So let's figure out, because these are in the Laplace domain, let's bring them back to the time domain. So let's go to the definition, right? So what defines a Laplace? So if you have, basically I gave you this conversion. So I said that x as a function of time is actually converted to Laplace domain via this way, right? So if we do that to every derivative, you get x of t, it's going to be s, x of s, e to the st. So these are the definitions that I gave you. And obviously you wouldn't have to do this every time, but I'm doing it here to illustrate what I'm trying to do. Okay, so this is how you convert displacement, velocity, and acceleration to the Laplace domain. And we did the same thing with the force, right? So we said that force is a function of time is this fs e to the st. Okay, so now let's grab this transfer function real quick, and I'm going to actually multiply through. So I'm going to kind of crisscross multiply. So if I bring this denominator, the 5s squared plus 20s plus 25, cross it up to multiply by x of s, I'm going to have this. So I'm going to have 5s squared x of s plus 20s x of s plus 25 x of s equal 3 f of s. Alright, so all I've done is multiplied through. So I've just done one algebra step. So now if you actually combine, and I'm going to let you figure this out, but this is really easy. If you combine these two things, you can quickly realize that this whole thing could be brought back into the time domain by kind of applying these relationships in inverse form. Right? So this thing becomes 5 x double dot. This becomes 20 x dot. And this becomes 25x. And this becomes 3 times f of t, because there's a zero derivative, so it's going to be 3 times 10 sine of 7t. So check out what happens now is when I actually do I'll just write it through, I have this new differential equation, x double dot, 5x double dot plus 20x dot plus 25x is equal to 30 sine 7t. Okay, so this basically now becomes my starting point. So notice that now I can say, okay, m is 5, okay, we got that. C is 20, K is 25, but what's different is that my F naught is no longer 10, now it's 30. Okay, so that's pretty straightforward so far. So now all we do is we're going to plug in the equations that we know we need to plug in. So we know we want to put it in this form, right? So we got to find x omega and phi omega. And if you go through your notes, you're going to find these two equations that I gave you early on. And basically one is that x omega is f naught divided by the square root of k minus m omega squared plus c omega squared. This is in your notes. It's also in the book. And you plug in all these things. You plug in k, m, omega, f naught, and that's going to give you that x omega is. I forget what the answer is. I have it over here. Yeah, 0.16. Okay, so if you do it out, you're going to get that. And the same thing with the phi. You just write out of the notes. This is going to be the inverse tan. And by the way, these are equations that I don't want you to memorize, so you'll have access to this. But you need to know where they are and where to find them. M omega squared minus K. So when you do this, you're going to find that phi is equal to, where am I? Yeah, same thing here, 3.71. So this is actually a much easier way to do it. But there's this kind of conceptual step where you have to convert it back to the time domain. It's up to you, whatever you feel more comfortable doing. Okay, hope this helps.